Hello, good evening. Thank you all for being here. I'm super happy and super humble. So today we're going to talk about one of the topics that I like the most in Unity, the topics that I feel more passionate about. So I hope you enjoy the presentation as much as I'm enjoying being here in front of all of you. Okay, so first things off, who here is a programmer? Can you raise your hands, please? Okay. Who is a technical artist in 3D? Okay, a lot of you. Who is an architect? Maybe a doctor? Not? Okay, cool. What we're going to talk about today is something that is really important, whether you're making a 2D or 3D game. But sometimes we consider this shader topic a bit difficult. However, it is not. If you're already programmers, or if you have some knowledge of how Unity works, how the material work, it's actually a super simple topic, and it's really fun to do stuff with Unity, right? So, my name is Arturo Núñez. I'm product evangelist for Unity. I come from Mexico City. That's my Twitter account. That's my personal email. Well, not my personal, my professional email. If you have any question regarding anything that we talk about today, please feel free to send me an email or a tweet or anything you might need. So let's start with a basic definition of what a shader is, right? If you go online and you type shaders or graphic shaders or how to program shaders, you probably will find different definitions. So for the context of this presentation, we will define a shader as a set of instructions that run on the GPU. The GPU is the graphics processing unit that comes into in our computers, our cell phones, game consoles, etc. Right? So let's start from here. The shader, what a shader is. Okay, so why do we want to write shaders if Unity has this thing called the standard shader that is supposed to work for almost anything that we want to achieve? Well, one thing, for instance, is since you're making different games than the rest of the community, you may want to achieve something special in your game, right? So maybe you are making an MMO and you want to have a lot of grass, but you don't want to animate using Maya or any other program, the grass, right? And you don't want to have a lot of animations to make the grass look real. So if you want to achieve something like this, let me play the video again. In this case, this was achieved using a shader. What we're doing here is we are just animating the vertices of our grass models during time, and we are achieving something that is faster than having the regular animation, because this is running on the CPU. Another thing where you may want to use shaders is when you want to achieve special effects for your games, right? This is a very common effect, a dissolve effect, in this case for Adam's mask. Sorry about the frame rate. So if you want to do something like this, maybe the tools that we offer in Unity out of the box are not enough. Or maybe what you want to achieve has a different style. If you were here for the Baobab presentation, maybe you will need to actually change the way Unity renders stuff. So that's it. That's when we want to mess around with shaders. So just as a quick recap, I want you to understand how Unity actually renders our scenes, right? So imagine when you're making your game in Unity or your project in Unity, you have a 3D scene. Even if that scene is a 2D scene, if you're making a 2D game, Unity is looking at that as a 3D scene. So by the end of the day, what we want to achieve is transforming something that is in 3D, a definition of vertices, points in the 3D space, to something that will end up as 2D, right? Something that will end up in your screen, your device screen, or in your headset, or whatever, right? So this is the rendering pipeline. This is a simplified version of the rendering pipeline. Let me try to see. Okay, so maybe it's a bit small. So basically, we start with a model, a mesh. In this case, it could be a triangle. And we will pass through two main programs inside our shaders programs. One is the Vertex Shader, the Vertex program. Remember that these programs will run on the GPU, okay? And the other program will be the Pixel Shader. So by the name, we can deduct that the Vertex Shader is the one in charge of modifying the vertices, right? So if you want to do something as the grass effect that I just showed you, then maybe you want to modify the position of the vertices, then that should go into the Vertex program. On the other hand, if you want to change the color of the pixel, either on screen space or on the model space, then you want to mess around with the pixel, right? You want to mess around with colors. So that will be in the Pixel Shader program, okay? So these are tied together. Unity will first start evaluating the Vertex program, then the Pixel program. That's the regular flow. There are more programs that can run. Also in Unity, we support them. For this presentation, since it's an introductory presentation, we will just stick to the Vertex Shader and the Program Shader. Just remember how these things work. Okay, so just another recap. We have Vertex Shaders. When we want to modify position of vertices, we cannot create more vertices. That's something that we need to consider. These programs will run in parallel, right? The GPUs are constructed via hardware to be efficient in the processing of a lot of data in parallel. So yeah, Unity will send a lot of vertices to the GPU and will receive transformed vertices depending on what you achieve there. We also have fragment shaders, which are also called, or sometimes you will see that in the documentation, are as pixel shaders. Also for this presentation, we will see them as the same thing. However, those are not the same thing. But fragment and pixels, in this context, consider them the same thing. And also, we will talk about surface shaders. The surface shaders is another approach of making shaders in Unity that basically allows us to interact with other stuff such as lighting in Unity without having to actually access the lights in our scene, etc. Everything is already there for us. But by the end of the day, if you are writing, and I will show you, if you're writing surface shaders, Unity will transform those as regular vertex and fragment shaders. So yeah, it's just another way to program, but by the end of the day, is going to end up as the same thing. Okay, this is just a recap. Also, I want to mention that the slides and the project that I will use today will be on GitHub, so don't worry, I will share that with you. This is just a summary of what I just said. What is the input? And what is the output on the Vertex shader, right? The same goes for the fragment shader. Here I just want you to notice that we have as an input something called fragment, right? And if we go a couple of slides back, we will see that actually when Unity is trying to see which objects or which colors it should render, those are called fragments. And we're going to transform them into pixels, into actual picture elements in a texture or in the screen. Okay? And the output is a color and the alpha of those pixels. Also, take into consideration that the fragment shader will run for all the pixels or all the fragments that we have visible at any frame. And the vertex shader will run just for the vertices. So if we have a model with, I don't know, 1,000 vertices, that program, the Vertex Shader, will run 100 times. If we have a screen with HD or whatever, you will probably be running that program millions of times, right? So take this into consideration. And this is the surface shader. Okay, so remember at the beginning of the presentation, I was telling you that this is not actually complex. Sometimes we think it's complex, but if you already know how to program, then you know a lot about writing shaders, right? Because you don't need to learn something new. The language that we use for Unity shading programming is called CG. And this is actually a super simple shader that just throws something white in the screen. We use CG, which is a language kind of similar to C. The G stands for graphics, so this is called the C for graphics language. That's the language that we use, and also we wrap the CG program within something called Shader Lab. Shader Lab was made by Unity. CG was made by NVIDIA. Okay. A couple of things regarding CG. It's similar to the C language. We will see that in a second. If you already know how to program C or C# or any of those languages, you will feel comfortable here. When we program shaders, most of the time we will be dealing with these type of values, right? Why? Because we're going to be dealing with position of vertices, position of pixels, colors, alpha values, etc. So most of the time you will be dealing with variables with 1, 2, 3, even 4 values, right? These things called vectors. To access the values there, we can do stuff such as setting color.rgb to access the RGB channels of that vector. Or for the same vector, we could do something like XYZ, and it will return us the first 3 values in the vector. And we can also do something called swizzling, which basically is accessing the components of the vectors in any order we want. We can do something like you see here, YX, we could do YYY, or anything that you might need. The important thing here is that we operate in parallel. What does this mean? That any, for instance, here we're adding two vectors, so Unity will do the addition in parallel. So this will be super fast. So, well, these are a couple of structures that we will see in a second. Let me just switch to my computer to show you the actual Unity code. Okay, so in this case, we have this Adam mask. You've seen this character before. It's from the Adam demo. In this case, I decided to keep the eyes just as a disclaimer, because if I remove the eyes, we get a creepy image of Adam. That's why I left the eyes. But we're going to focus on the face, right? We're not doing anything super fancy. We're just drawing a red color. We're just tinting the mask to red. And I'm doing this to show you how the shaders work, right? This is the shader that is a program that is actually making my mask to be painted into red. So the basic structure of the shader in this case is really simple. Here we define that we want to use this name for my shader. It's called shader 01. We can have one subshader. In this case, for all the examples here, we're just sticking to one subshader. Sometimes you will find that your hardware doesn't support a shader, so you may want to have a fallback, and you probably have seen that if you have opened any shader in Unity. Then we declare some extra stuff for Unity. Everything from here to here is Shader Lab. This is the way to communicate between my program and Unity, right? I'm just telling, okay, this geometry, I want it to be rendered on the opaque pass, so that's what I'm doing, meaning it won't have any transparency. Here, we see that we are actually starting the CG program, the program that actually transforms the vertices and pixels. Here, we have two pragmas. And basically what I'm doing here is I'm telling CG what program, what function, from the functions I'm going to write, is going to be the vertex program, and which one is going to be the fragment program, right? So I said pragma vertex, and this vert name here is going to be my vertex function. On the other side, we have the pragma fragment, and frag will be the name of my fragment function. So it's actually really simple. And where do we have those functions? We have them here on the same program, on the same CG section. So as you can see here, I have the vertex program and the fragment program. What we get here as an input on the function is something called appdata underscore base. That's already declared in CG. So if you go to the documentation and you see that, the explanation is actually not really clear. So just for you to know, I will go back to my slides. If you use this app database to pass data around, we will be passing around a position, normal, and a text coordinate. We will see this in a second. Just for you to know that this thing sometimes looks like magic because we don't see where that comes from, but it's actually declared in here, this Unity CG include file. Okay, let's continue. So as you remember, I mentioned that Unity will execute first the Vertex program and then the fragment program. So what's going to happen here is that we will execute this Vertex program and then we will execute this fragment program, right? And to pass information from one program to the other, we need to use a data structure, right? In this case, we declared something here called B2F. And this is also really common when you see in shader documentation that this B2F, and you don't know what that means. Basically, it's the short for vertex to fragment, right? So if we want to pass information from the fragment, from the vertex step to the fragment step, that's why we use this name, but you could use any name you want. In this case, the only thing I'm passing around is the position. Okay, so I just want to pass the position of my vertices into the fragment program. What I'm doing here in the vertex program is really, really simple. I'm just declaring this B2F object. Then I set the position of that object, but I'm using a clip function. Why do I do this instead of just returning the position of my vertex? We're doing this because, remember, we have a 3D scene. And we want to transform that into a 2D space. So basically, that function over there gives us the result of the projection, right? So if I have, let's say, at any point on my screen, I want to see where that point corresponds to, I don't know, a screen on the computer where we're streaming the video. Well, that's what is going on. Okay, and finally we return the vertex, the result of the vertex. We're not doing any transformation besides the projection, so we're good there. And then we will run, remember, per each visible pixel, we will be running this fragment function. In this case, you will see that we're returning a half-4. We're returning a vector of 4 values with half precision. And here I'm returning this color, which is, remember, RGB and A. What does this return? Red, right? A super, super weird red. And this is what we're seeing here in this point. Light doesn't affect because we're telling Unity directly, render a red color there. So if we want to change this mask to have a color, let's say like green, you get what we want to do, right? We're going to set this value to 0 and this one to 1. So let me do that real quick. We're messing around with the RGB values. So we have a green mask, a pure green mask. You can do combinations, etc. Just remember, if you start seeing these things, sometimes when you go to the color picker in Unity, you will see the color space, the color range from 0 to 255 for the colors components. In this case, we need to stick on the range of 0 to 1. That's what you need to remember. Okay, this is the basic shader. Doesn't do anything fancy, but we're starting to see what's going on, right? Like, if I want to change the color to do some crazy things, well, we know that we can mess around with the fragment function and just operate over a vector and return that as a color. So it's actually very simple. Let me open another scene. And in this scene, you see that I have a creepy version of Adam's face. What I'm showing here, and let me go back to the shader. Well, the program is the same, is the exact same thing. When you create a new only shader, you will get this base, so don't worry about memorizing these things. Just remember what these things are, but that's it. Okay, the struct here is the same. However, instead of messing around on the Vertex on the fragment program, we're going to be doing transformations in the Vertex program. So in this case, you see here on the lower part of the screen that we are multiplying the position of the vertices on the Adam's face by 0.70 times, which means we're scaling the vertex position, right? That's what we see over here. We have a scaled version of the mask of Adam, but we are not doing that using the actual transform over here. You see here that the value of the face is 6.14. In this case, we're just via shader doing that transformations. Okay, this was just to show you how we can do stuff on the Vertex program, right? To move around to transform the vertices in our models. Okay, let's go to the third scene. For this one, I need to hit play. This is super simple, but also I think it's important to see what's going on here. And when you are writing shaders, a lot of times you will be messing around also with the mesh information, with the actual model information. So in this case, this object over here is not there. It's just an empty game object with a script. When I click play, this object gets generated. So let me just show you how I'm generating this. I'm using another script. This is a C# script. What I'm doing is procedurally generating a quad. I could be creating any model I want it. But yeah, what I'm doing here is I'm generating a quad. So as a quick summary, I'm here creating a mesh, and I'm setting the values of the vertices by hand. So I'm telling I want one vertex to be here, another here, and another here. Then another interesting thing that sometimes it's not super clear is that we can also store information, color information in our vertices, right? So if you want to do some coloring stuff, you can actually store information in the vertices. So I have, per each one of the vertices that I have over there, I have stored these colors, and you will see later what I'm doing this. And finally, here, I'm defining the triangles. So let me go back to Unity again, and let's see what's going on over here. So I hope you can see on the scene view, I have two triangles, and what I'm doing is generating the quad using C#, and you see this coloring over here, right? Basically, the colors are the same. You see red, green, blue, and gray. So we have here red, green, blue, and gray. Another thing that we need to understand here, and is very useful, is that, okay, let me ask you this. If I go to the backside of my quad, I don't see anything, right? And the response most of the time is, oh yeah, because the normals are pointing somewhere else. However, I'm not calculating any normals here. This object doesn't have any normals into the actual object. What really matters when Unity needs to decide whether to draw a triangle or not is the order on which the triangle was generated, right? If I use the reverse indices here, I will have the quad facing the other way. So just make sure that you remember this. By the end of the day, yeah, the normal will get calculated using also the vertices, but in this case, we don't have a normals, right? So what actually matters is where the vertices here are. So let me open the shader, number 3 here. We have the same structure. Everything is the same. However, here in my vertex 2 fragment structure, remember, this is the object that will be used to pass data around. I added a color value. I will be passing around the value of the color that I have stored on each one of those vertices. Okay, because I want to use it to actually color. So here on the vertex program, I'm not doing any transformation to the vertices, but I'm actually passing around the color, right? And finally, on the fragment function over here, I'm telling, okay, return the color for each pixel, right? But we have 4 colors stored, 1 color stored on each one of the vertices, and we have thousands of pixels on this quad here. What's happening? Well, Unity, under the hood, is actually interpolating the values. So if we know that a color over here is fully red, a color over here is fully green, then something over here should be a value in between, right? So this interpolation, it's being calculated by Unity in a super fast way. So this is what we're seeing right now, okay? So yeah, I just wanted to show you here the mesh API, how we actually, how Unity interpolates the color values, because we don't, it will be hard to actually tell Unity, I want you to paint this color on this specific pixel, because also the objects are moving, the camera is moving, so it's I will say, probably impossible to do that. That's why we are programming stuff to get rid of having to do that manually. Okay, so let me open another scene. So if I click play. Also, another example that is not super fancy, but is useful to learn another concept. In this case, we see that this quad is totally white, and I don't have any light in my scene. So if I go somewhere here, I see that I don't have a light. I have a camera, a mask that is deactivated, the quad, and something called fake light. If I click on that fake light, you see that this is just a transform with some script, but it's not actually a Unity light. However, if I rotate this empty game object, it kind of behaves like a light, like a directional light in Unity. But it's not a light, we're just faking that thing. And of course, it's better to use a Unity lighting system for most of the cases, but I want to show you a couple of interesting things here. So the first thing is, sorry. I think I skipped one step, yeah. This is important. Sorry, let me go back just one step. So here we have the face of Adam again. This is shader number 4 here. In this case, it's again super simple, but we introduce another concept, and it's a really important concept because we want to give the artist or whoever is defining the materials the freedom to actually modify properties in our shaders, right? So just for this example, I have added Appropriative Look, which is this new part of code where I define variables that will be visible in Unity and that I will be able to change within Unity. So to have a variable to modify stuff in my shader program, I just need to do something like what you see here. I define the name within the program. Here I define where it says red value, the text that will be shown into the editor, the value type. In this case, I just want to store a float value, and the default value over here. When I have that, if I go to Unity, in my material, I will see the properties that I declared here, right? Another thing that you need to remember is that, okay, you have those properties exposed in the editor. However, if you want to use them inside your CG program, remember this section over here, you need to declare them in that scope. So what I did is just declaring the variables with the same name. That's important, otherwise Unity won't be able to connect them. And yeah, that's basically what you need to do. It's a bit verbose, but yeah, is something that is needed. So in this case, what I'm doing is just allowing the user to change the RGB channels of my mask. So I could do something like 0.5, 0.5, 0.5. And now I'm allowing the user, instead of the programmer setting the color in the code, I'm allowing the user to set that in the editor. For colors, you may want to use an actual color picker. I just wanted to show you in the simplest way how to expose properties. Okay, now to the example that I was showing you, which is this one. I don't have a light, again. I just have this fake light game object that if I rotate, makes the object seem as if it were illuminated by a light. But I want to show you two things. One is that within C#, I can set properties also from our shaders. So if you're doing something and you on the C# side and you want to set values to your shaders, you can use the shader class and use something like the select global vector. In this case, I'm using a property that I declared in my shader called light dir, and I'm sending the direction on where this object is facing to. So this will be available for all my shaders across my Unity project. You may or may not want that. But yeah, okay. So again, the same shader program. I'm just adding a couple of extra lines of code. In this case, I declared my light dir float here. It's a float tree, which means contains three values. But I don't need that declared here. I don't even have a property block declared here. Why? Because I'm setting the value of that property using C#, using the shader class directly. What I'm doing here also, I'm actually calculating the normal value of my quad. Remember, we were before I mentioned our object doesn't even have a normal. We are now setting the normal value. And finally, we're doing quick computation, basically to see if the light object, remember it's a fake object, is perpendicular to the plane or to the quad, then that value will be equal to 1. Which means it will be rendered in full white because we're multiplying here by white. On the other side, if the fake light is parallel to my quad, then that will return a 0, which means this vector will turn to 0, which will be black, right? So this is how. Well, no, this is not how Unity calculates the light. We have more advanced stuff going on. But yeah, this is the basic idea. And you will be dealing with dot products, cross products a lot. So I will recommend you to take a look at the Wikipedia page for the dot vector product and the cross vector product. Not to the actual way of computing that, because the functions are already there, but to actually learn what those mean, right? Like, okay, if I want to do a comparison of two vectors, which function should I use? But yeah, you don't need to know how to calculate that if you don't want to. If you want, then could be great too. Okay, next thing. Now we have the same mask, but we are using a texture. Again, these are simple examples, but I think it's worth knowing what's going on behind the scenes. So let me open the shader 7 over here. We have now defined a different property. In this case, I'm using the 2D data type which stands for a texture, a 2D texture, and I'm setting the name as main texture. That's what allowing me to set a texture here in the material properties, right? If you have used materials, it's pretty much the same, and we recommend you to use the same workflow, because if your users or if your teammates know already the workflow of Unity, it's better if they can use the tools that they already know, or a tool that follows the same workflow as they already know. Okay, so we define that thing over there. We're passing around the position, but also we're passing around a UV coordinate. And I will explain to you that in a second. From the Vertex program, we're passing around, again, the position and a UV coordinate. And here, on the fragment, where we are deciding which color to actually paint, I'm saying, OK, the color that I want you to paint is whatever is stored on the texture on that UV value. So what's this UV thing? If you have used 3D software before, maybe this is something that you know by heart, maybe not. So I will try to do my best to explain to you how this works. So when we're modeling 3D objects, we end up with triangles. We end up with polygons, and we want to map 2D textures to that 3D defined object. So for that, we use this technique called UV mapping, which basically does something like this. And again, I'm going to do my best to explain how this will work. Okay. So imagine we have this 2D texture, and we want to map a part of this texture into a 3D model. So basically, what we have is the vertices somewhere here, and the connection between the vertices will give us, again, a triangle. And that triangle here might be a triangle that is over here, right? We're not setting pixel by pixel the relationship between the texture and the 3D object. We're defining just where the vertex should be in the texture. And again, Unity is doing the interpolation. That's why here in our shader, we're just telling, OK, whatever you have on the B2F structure, whatever the value corresponds to the texture, then bring me that color, because I'm going to draw using that color. That's, in a nutshell, how this thing, the UV mapping will work. This is, I think, one of the most important concepts to know, how do UVs work, because if you just go to the web and download an object, and you try to apply randomly a texture, if the object doesn't have the UVs unwrapped, then the results will be weird. So it's important to know that it's not the fault of your program, maybe because the 3D model that you are using doesn't have all the information that is needed. Okay, so number 8. Now, I do have a light here. If I rotate the light, you see how we have a nice shaded version of the Adam mask. And what's going on here? The only difference is that I actually have a light. But if we go to the shader, number 8, we're actually declaring here a surface function. Remember, we were declaring and using the vertex and the fragment functions. Now we're just using a surface function. This surface function, by the end of the day, will be converted automatically to a fragment and a vertex functions. But using this technique or using this approach, you will be able to mess around with lighting and some other stuff that comes with the Unity physical-based rendering. So yeah, it's easier to interact with light, for instance. So as soon as I'm doing this, as soon as I'm declaring the surface function, I need to change the way I'm passing around the data. The difference is that the input over here, it's a bit different. But instead of returning a color or returning a vertex position, here I'm just setting the value to whatever my source face output structure is. As you can see here, there's no return value. I'm just setting the albedo value to whatever I have on that texture. Also, here, I made a quick change. Instead of defining pragma vertex vert, I'm defining the surface function, which is called surf, over here, which is the same one as the one here. And I'm defining a lighting model. In this case, I'm using a simple Lambert model, but you can use the standard lighting model in Unity. So remember, this will end up as actual vertex and fragment functions, but we don't need to care about the verbosity of writing the two different programs in separate. Okay, so in this case, I'm just setting the albedo property, which is the color. I'm just setting the color to whatever I have in the texture. So the UV mapping happens the same way. However, I get all the lighting, all the cool graphics stuff in Unity, and I don't need to do anything else, right? So if you want to make use of whatever Unity offers you on that regard, it's good to have a surface shader. Let me go to the next example. In this case, what I have here is a vertex animation. I'm just animating the vertex positions of Adam's mask during time using a fragment function. But also, this shows us, yeah, this one. Well, the same things are the rest of the code is basically the same. Remember, we defined a surface function, the lighting model, but I also defined, I told Unity, I want to actually do stuff on the vertex program, so I'm going to define my own vertex function. So in this case, when we're using surface functions, you will use a vertex semicolon vert instead of the other way of doing that. And the vertex function that I just defined, I'm just doing some computation to animate the vertices of Adam's face based on the normals, right? Similar to what I did with the shader, with the grass example, but in this case, to a more complex 3D model. Here I'm returning, again, just the color of whatever I have stored on my texture. Back to what we were talking about. Here. If we're using surface shaders, we can also assign stuff to our Unity objects. So in this case, I'm using the same thing. Everything is the same. But I'm also setting the, oh, this is not. Wait, I was using an incorrect shader. This one over here. Okay, so I'm also allowing the user to actually modify the emission of a given object. So if I go here, let me go back to my layout, select my camera, my mask. You see how we are using a second texture, because I have one texture being the main texture, I have another being the emission texture, and I'm just setting the values of the emission directly using another texture. You can use also another texture if you want to do something like masking, but in this case, I'm just modifying the emission value on my Adam's mask. Finally, to have something that actually resembles a game. All that we learned right now was just, I will say, like less than 1% of what is there to learn about shaders. And basically, I say that because, okay, you can know all the syntax, you can know all the rules of writing shaders, you can know a lot. However, to me, the difficult part here is to imagine what do you want to achieve, right? If I tell you, oh, can you write a shader that makes the stage look like it's made out of jelly? Okay, you might know how to program that because you know the syntax and etc. But you need to start thinking, okay, how does jelly behave? How the light should be reflected or should be absorbed? How the color should be transformed? Should that be animated? Does the color of the jelly is actually important to anything, any of these? So I think that's the difficult part, knowing what do you need to program, not knowing how to program that. So in this case, this is a simple hologram shader achieved with this, with just whatever we saw today. So we have some animation of the textures. We're moving around the UVs, etc. Yeah, this is a super simple effect, but we would like to see what you come up with. And just to close, here's the link to the repository. Everything there is available for you. You can get it. The slides are also there. I think it's, if you're interested in this part, shader programmers, shader professionals, technical artists who knows the basics of shader programming are something that the industry needs. And you don't need to actually code everything. There are tools such as an Amplify shader editor that you can use to program visually. But again, the hard part, at least for me, is knowing what do you want to program. A couple of extra references. This is a super nice computer graphics online course. I will recommend you to take a look at it. There's also a YouTube channel from a guy that recreates effects from other games into Unity. And he also gives you the source code and the examples. So it's impressive what this guy achieves. More information, more tutorials, and this thing, the last thing over here, the shader toy, is actually not Unity related, but if you want to get some inspiration, I will recommend you to go to shadertoy.com and see what other people are doing in shaders. And of course, you can do that in Unity. And we don't have time for questions, so I will leave the slides and demo link over here. Thank you very much. I hope you had fun, and I hope you learned something new, and see you around. If you have any questions, I will be the rest of the day here. So thank you.